Okay, I'm really glad to introduce Logan Hyslop with his talk, Introduction to Analytic Geometry. Please.
All right, so today we're going to talk about condensed math and some analytic geometry. So if we're going to talk about condensed math, the first thing we should know is, well, what is condensed math? So let's go ahead and start by defining some sites. So this is in the sense of like a Grothendieck site in algebraic geometry. So we have the site profine. Let's call it profine, profinite sets, or it's the category profinite sets. And where the covers are finite families of jointly surjective maps. So if you don't remember what a profinite set is, let's talk about that for a few minutes. So profinite sets. A profinite set is a formal inverse limit of finite sets. So a pro object in the category of finite sets. Equivalently, we can describe these as objects in the category of topological spaces. So it's the full subcategory of top consisting of those, we'll say consisting of compact Hausdorff totally disconnected. So this just means that the only connected components are points. Spaces. So what are some examples? Well, we have the p-adic integer ZP, our classical example of some profinite set. We have the set of the natural numbers union a point at infinity, where the topology here is discrete. And over here, the open sets which contain this are just this and the cofinite sets. So this is just the 1-point compactification of the discrete natural numbers. So this is some profinite set. And for a third example, we have a very important class of examples is beta S for S set. So beta S is a stone check compactification. Of a set S, which is some sort of a universal compact Hausdorff space. In particular, it has the universal property that set maps from S to, let's call it C, are equivalent to topological space maps. Actually, let me specify this so you know where C lives. So maps of compact Hausdorff spaces, C is some compact Hausdorff space, from the stone check compactification of S to C. Okay. This leads to our next definition. A profinite set S is called extremely disconnected if it is projective in the category of compact Hausdorff spaces. So what does this mean? This means that every surjection from a compact Hausdorff space splits. You can also equivalently define this as some profinite set where the closure of every open is closed, but that definition is less useful and it takes a little bit of work to show that they're equivalent. So I don't think we'll ever actually need it. So we're just going to stick with this definition here. All right. And some examples of profinite sets. Well, of extremely disconnected sets. So the prototypical example of an extremely disconnected set is just our example from before, the stone check compactification of a set S. So why are these extremely disconnected? Well, if we have some surjection from some compact Hausdorff space to the stone check compactification of S, then we can just choose some set theoretic section of S living in here. And this is going to induce a map from this map on S to C to, here, let me draw it like this. This is going to induce this map here. And since this is a set theoretic section, S going into here both ways are both the identity on S. So this is going to be the identity on beta S by the universal property. Okay, and in fact, all extremely disconnected sets are retracts of stone check compactifications. This is just since if you have some extremely disconnected set, call it X here, then you can take X as the underlying set, and then you take the stone check compactification of that, and this is natural surjection this way. And since it's extremely disconnected, this splits. Okay. So now that we have that out of the way, we can define the site of extremely disconnecteds. This is going to have objects or extremely disconnected sets and covers jointly surjective finite families of maps. So equivalently, you can take some finite product of these and this is still going to be an extremely disconnected. So you can just, if you have any finite jointly surjective family of maps, you can just take the coproduct of the sources, and then this is going to give you some surjective map between two extremely disconnecteds. This does not necessarily have pullbacks, so it's not exactly a site in the classical sense. There's a little bit of a technicality, but you can still define everything like you normally would. Okay, so the last site that we will consider is the site of compact Hausdorff spaces with finite jointly surjective families of maps as usual. So these are the three sites that we're going to use. In fact, sheaves on each of them are equivalent, and that's what we're going to use to define our condensed objects. So definition: a condensed set, abelian group, etc. You can just take any object in some category C, is a sheaf, put a star here, of sets, abelian groups, etc. Object in some category C on profinite sets. Equivalently, extremely disconnecteds and C-house, compact Hausdorff spaces. All right, so why do I have an asterisk here? Well, the asterisk here is because there's a few set theoretic issues. If you define it explicitly this way, you can fix, these sites are big, so you really don't want to deal with any set theoretic issues that come up there. There's two ways to fix it. One way is the way Peter, Hain, and Barwick, I believe, take it, where you just fix some universes and then consider these in some smaller universe. And that gives you what you call the pyknotic approach. So pyknotic sets, pyknotic abelian groups, some pyknotic category. The way Schulze and Clausen do it is, instead of doing that, you fix some cardinals kappa and you consider the site of kappa profinite sets and you consider sheaves on those. And then you build it up through all kappa and you have some adjoint functors between them. And then in the end, you just take a co-limit over things that live in one of them and are stable under all of these functors. So this gives you a way to get around those set theoretic issues. We're not going to talk about that much today. I just want to point out that they are there. All right, so what this means is explicitly, so it's some functor f from profinite sets up to your category C, such that f of S coproduct with T is equal to f of S times f of T. And if S to T is surjective, then f of T is going to be the equalizer of f of S x f of S to f of S x Ts. Here, just remember that pullbacks are to be thought of as taking intersections, and that's about all you really need to know about thinking about sites in order to translate anything from classical topology into site theoretic language. All right, so why do we have these other sites? Well, we won't use compact Hausdorff spaces very much because that's kind of not a nice site to deal with. We will use extremely disconnected a lot because since every surjection is an extremely disconnected split, you don't have to worry about this gluability axiom. So equivalently, you have some functor from extremely disconnecteds up to C, such that it takes finite disjoint unions to finite products. F of S coproduct T is f of S times f of T. All right, so why might this be useful? Well, we can embed topological spaces fully faithfully into condensed sets. And this is actually not literally true, again, because of set theoretic issues. In fact, this comes up if you have a topological space which is not T1, then there is going to be some issue where you don't actually get a condensed set out of it. So really here we mean compactly generated weak Hausdorff spaces of Jarl T1. And so how do we do this? Well, we take a space X is going to go to the condensed set of maps into X. And this is sort of like a Ionetta type argument. All right. And conversely, given any condensed set, we call it T, a condensed set. We can get a compactly generated weak Hausdorff space just by taking T on the point, and we're going to equip this with the topology as a formal quotient of all of the T of S's. I'm not going to spell out all the details for that. You can check Schultz's notes in order to see how to do that. All right. So let's shift and talk a little bit about these form an injunction. There's an injunction in topological spaces and dense sets, and we're not going to harp too much on that. So next, let's talk about topological abelian groups, or rather condensed abelian groups. All right, so in condensed abelian groups, what does the story look like? Well, these are just going to be sheaves of abelian groups on these sites, and we're going to have some important objects that we'd like to consider. We have an internal hum. So given condensed abelian groups A and B, we can form the object hum underline of AB, where, okay, I'm not going to do the underline, I'm just going to call it hum because I don't want to draw that constantly. So hum, okay, that's all right. I should do the underline, sorry. All right, so we're going to form hum AB, where hum AB evaluated at some, say, extremely disconnected S is just going to be hum of A times Z of S to B. Here, Z of S is the free abelian group on S. So the free condensed abelian group on the extremely disconnected set S considered as a condensed set. So this is coming from a free forgetful adjunction between condensed sets and condensed abelian groups. So this just means that we can take these on these sets here on anything. All right. And then we also have a tensor product by sheafifying the usual tensor product. Or you can also get it formally as an adjoint to the internal Hom. Okay. And let's talk a little bit about these Z of S. So a common theme in condensed math is looking at compact projective generators. What do these mean? So here we're talking about in some abelian category. In this case, the category of condensed abelian groups. So projective says that Hom P dash commutes with taking co-kernels. So this is going to behave nicely with respect to quotients. Equivalently, any surjection to its splits. These all work out well. And compact says Hom P dash commutes with colimits. So how do these apply in our case? Well, if we take S extremely disconnecteds, sorry, X an extremely disconnected set, then Z of S is compact projective. Now, why is this the case? Well, if we look at Hom from Z of S to some condensed abelian group A, well, this is just isomorphic to condensed abelian group, condensed set maps from S to A, which is just isomorphic to A of S. So we need to see that taking these S-valued sections actually does commute with colimits, and that will be enough to show these two parts of this claim. So in order to see this, note that in abelian groups, product equals coproduct. So we can always calculate these colimits of sheaves by first taking the colimit and then sheafifying, because the colimit might end up somewhere in pre-sheaves and might not actually be a sheaf. So what we need to show is that the colimit actually does give us back a sheaf. Well, if you remember the definition of a sheaf on extremely disconnecteds, it was that f of s coproduct t is isomorphic to f of s times f of t. But since here, product is the same thing as direct sum, it's a colimit in particular. So it's going to commute with all colimits because colimits commute with each other. So that means that when you take the colimit of these sheaves F, you actually get back a sheaf. So the colimit can be computed pointwise on these extremely disconnecteds, which tells us precisely that Z of S are compact projective generators. Generators just means that everything is a formal colimit of some of them. All right. So we can actually define the category of the derived category of condensed abelian groups as usual. I will add a note here. Although condensed abelian groups has nice projective generators, it has no non-zero injective objects. So this just tells you have to be a little bit careful when trying to compute derived functors. It's fine if you're trying to derive in a way that you can use projectives to do it, but you can also worry a little bit about if you want to try and write derive some stuff, how that might go. So you really need to be a little bit careful with that. All right. So in particular, one useful thing there, I'm not going to harp on this story, I'm just going to mention it. Locally compact abelian groups. If we have locally compact abelian groups A and B, we can consider homomorphisms from A to B in topological abelian groups. This is an internal hom considered in the compact open topology. And then we can go ahead and condense this. So this underlined here, by this I mean I'm taking the condensed abelian group on these topological spaces. Now this is canonically isomorphic to the condensed hom of their underlying condensed sets. And in particular, you can even show that, so you call these LCA groups. This is the category of locally compact abelian groups. And I forget exactly who it is, but somebody has a paper on looking at their exact category that they generate and then defining the bounded derived exact category on that. And you can prove that that bounded derived exact category embeds fully faithfully into the derived category of condensed abelian groups. Here, the derived category is just some either triangulated category, or you can think of it as some stable infinity category. It doesn't really matter, both work. All right. Later on, we will actually not use it as a triangulated category. We will use explicitly stable and pre-stable infinity categories in order to actually make some arguments. Okay. So the next thing that we define in the theory is analytic rings. So what is an analytic ring? So a pre-analytic ring first is a pair A, M, where A is some condensed ring. I'm not specifying that it has to be commutative here. When we get to some part later, we will add some commutativity restraints, but for this part of the theory, we don't need commutativity. Where A is some condensed ring and M a functor of measures. On A. So in particular, M is, so this means that M is a functor, extremely disconnected sets to condensed A modules. So these are condensed A modules in condensed abelian groups, which takes a extremely disconnected S to something which we call M of S, together with a natural transformation of condensed sets from the extremely disconnected S to, this is here considered as a condensed set again. I won't usually distinguish between considering them as a condensed set and as a topological space, because again, topological spaces, nice ones, embed fully faithfully into condensed sets, so there's not really anything to distinguish. So we have this natural transformation here, and equivalently, a natural transformation of A modules from the free condensed A module on S to M of S. All right. So this is going to give us some notion of what we're going to have is some ring together with some nice measures on it. And the modules here that we're going to get out of it are going to be those which are complete with respect to the functor of measures m, in some sense, is what we are trying to define here. But we need some more conditions before we can actually do that. Again, this is just a pre-analytic ring. So what is an analytic ring? An analytic ring, AM, is a pre-analytic ring such that for all complexes, C star, where Cn is a direct sum of copies of M of S for varying S, we have that the natural map from R hom in A modules of M of S to C to R hom in A modules from A of S to C. So A of S is just your free group here. This is where this is coming from. Is an isomorphism. So this just says that our M of S are precisely the free objects in some nice category of C. So next we define for an analytic ring AM mod AM as the full subcategory of mod A modules, such that the above map is an isomorphism. Similarly, can define derived category of AM as the full subcategory derived category of A modules of those complexes such that this here is an isomorphism. And objects in that category are going to be precisely those with all of their homology groups in this one. Oops. And what is useful about this? So by our conditions that we imposed, these formally imply that AM modules, respectively, derived category of AM modules, are closed under all colimits, limits, and extensions which exist in mod A, respectively derived category of A, and the M of S are compact projective generators. Furthermore, we have a junction. I'm going to write the derived category version. You can also write the standard version on modules underlying it. Instead of writing a left-right functor for the tensor, I'm just going to write the tensor because we're just going to work with derived objects here. But you can write the same story in the abelian case, just changing a little bit of what I'm saying. So we have here what we're going to call tensoring over A with AM. And here we have a fully faithful inclusion. So if you know localizations of categories, the right adjoint being fully faithful means the left adjoint is a localization. So what we're saying is that this down here is precisely a localization of the above category, which we might consider as completing with respect to the measures above. All right. So what are some examples? Well, there's two sort of prototypical examples. So prototypical example one. Our first prototypical example is solid. So what is solid? It's going to be what we call Z solidified. So in particular, Z solidified of S is the formal inverse limit. So if S is equal to the inverse limit of SI, where SI is finite, this is the formal inverse limit of Z of SI. Equivalently, you can define this as hom from the free abelian group of continuous maps from S to Z to Z itself, so some sort of dual here. This is what you might call the Z-valued radon measures, if you've heard that term. It's an analysis term on S. Okay, and we can see, in fact, that this is isomorphic to a big product of copies of Z. So solid is also defined. Solid is the module category for this analytic ring. And the subcategory of condensed abelian groups that solid determines is the full subcategory. It's the smallest full subcategory generated under limits and colimits by Z. There are some nice properties you can talk about with solidifying certain objects, and we're going to mention one or two of these later. The other prototypical example is going to be what we, well, actually, let me expand a little bit more on the solid story before I move to the liquid story. What you can do is, after you prove that this works and actually does give you some analytic ring, you can expand this and actually show that we have more analytic rings associated to any Huber pair, or any discrete Huber pair at least. So if A plus is a discrete Huber pair, then it determines an analytic ring. Well, you might be asking, what is a discrete Huber pair? Now we're leaving the world of analysis and going more towards number theory. So in particular, arithmetic geometry. So a discrete Huber pair I say discrete here because we're talking about discrete rings, is a ring A together with an integrally closed subring A plus. So what we should think of this as is A is going to be some ring and A plus is its ring of integers. So some prototypical example might be the p-adic rationals with the well, I guess this one you would really want it to be, this is an example both of a non-discrete Huber pair, and because you can always just take discrete topology in both these a discrete Huber pair. Normally you would think of this as a non-discrete Huber pair, but it still works as an example of a discrete Huber pair. even though for defining the modules, you actually probably want to use the non-discrete version. So you might also have some examples of QZ or something of that form. And you can create a so-called adic space, A+. This is going to give you something called an affinoid adic space. Really a discrete affinoid adic space, but whatever, on some discrete Hilbert pair. So the way you define this is in classical algebraic geometry, you're using prime ideals. In this case, you're not using prime ideals, instead you're using valuations. So certain valuations, if you know the definition of multiplicative valuation, it's a multiplicative valuation on A, except you don't require that something is zero if and only if something is value zero if and only if it's zero, because you might want to have to quotient some stuff out, which is what allowing other stuff to be zero gives you, such that the valuation on A+ is less than or equal to 1. So here you're taking value is in some arbitrary written multiplicatively ordered abelian group. And A+ is going to be something which you always want to land in the ring of integers defined in the usual way of whatever you have at your stocks. All right, and you can globalize. To get discrete adic spaces. So in the exact same way you would in normal algebraic geometry, and using some nice tricks with, you don't want to use derived categories here because derived categories don't glue very well. Instead, you move to the stable infinity enhancement. You can either stay there or you can quotient back once you do the gluing, but you can show that you can associate to any discrete adic space X is OX, OX plus. You can associate the derived category OX, OX plus as some condensed derived category. All right, and the last prototypical example is going to be something from real analysis. So what we want to do here is we want to try and embed Banach spaces, which you might remember from your undergraduate analysis courses. We might want to try and embed these into the condensed language. But something bad happens in that if we look at the real numbers and we try and solidify them, we get 0. Even the left derived functor of the solidification is 0. You don't get anything back from out of it. So this tells us that while the solid world is very good at handling non-Archimedean analysis, it is insufficient for Archimedean analysis. So this leads us to want to try and do a very similar thing to what we did before. So what if we try and consider radon measures on some S valued in R? So our naive definition might be M of S is a limit over radon measures here. But does not work. Actually, let me undo that because we're still going to keep this definition, but this does not work well. This does not give an analytic ring. There's some extension problems that you can explicitly show. So we want to know what we can do to fix this. We can end up defining these explicitly in terms of an inverse limit of certain measures on our finite sets, and this for varying values of p. So this is going to fix some 0 is less than p is less than or equal to 1. Now we might want to try and talk about certain p-complete Banach spaces, or what are classically called p-Banach spaces, which are some refinements of Banach spaces which are a little bit more general. So for this, we're going to define MP of S as the union over all C is greater than 0 of, so here S is some inverse limit of SI, MP of SI. Actually, let me make sure I'm consistent with Schultz's notation for this. We actually call this R of SI. LP is less than or equal to C. So how do we define these things? Well, here SI is some finite set. LP is less than or equal to C. This is just going to be defined as the set of AS over S in some finite direct sum of copies of R, such that the sum over all S and SI of absolute value of AS to the P less than or equal to C. So here we're thinking of some sort of assignment to each clopin some measure such that the LP valuation of it, so the norm in the LP is going to be less than infinity, which is really what this here is going to give us. But this again does not work. MP of S suffers from similar extension problems. However, the situation can be saved. So how are we going to save this situation? Well, what we can do is we simply allow ourselves to define M as less than P. So M is less than P of S is going to be defined as the limit over P prime is less than P of MP prime of S. Note that we have a map from MP prime of S to MP of S whenever P prime is less than P, just since here you might as well consider all of these AS's being less than 1 because you can discard the finitely many which aren't. And then for P is greater than P prime, both less than 1 or less than or equal to 1, these are just going to be smaller when you take the bigger P because these are all less than 1. All right. And then it's a theorem of Schultz and Clausen that R M is less than P of S is an analytic ring. This is a long proof. If you've heard of the liquid tensor experiment, they spent over a year, I believe, formalizing this proof. The lean people did. And so this has been completely formalized and checked. It's probably 30 to 40 pages of analytics.pdf that this takes up. It's hard to. So it might be worth skipping it on the first reading. Okay. So this is nice because now we can import Banach space dot PDF into condensed world. And you can show tensor products of Banach spaces in the condensed world. These, okay, this is actually not in the liquid modules. This is actually in a different category, which is not abelian, but this is just sort of a side note. These coincide with ones defined by Grothendieck. Okay. And we call the category associated to these lic P for P as above. Our P liquid vector spaces. Well, now that we've seen that we have a way to import both Archimedean and non-Archimedean analysis into this framework, this is a homotopy theory seminar. So why aren't we doing any homotopy theory? Well, that's a good question. We can do some now. So let's add one more example, or let's do a few more. I'm not going to go into all the details on all of these, not that I've been going into the details on the ones before, but we can also define these things over spectra. In particular, we can talk about solid S modules. Where S is the sphere spectrum. And what we can do is if you let K of C be algebraic K theory of C, where this takes values on S as the K theory spectrum of continuous maps from S to C, then you can look at K of C, you can solidify this, and you're going to get back the spectrum KU, connective topological K theory. And you can do a similar game where you can talk about liquid modules. In particular, there's a way you can talk about liquid modules. This is actually how you go about proving that the R liquid case works. Z of P is greater than R, for 0 is less than R is less than or equal to 1. You might want R less than 1, actually. R something between 0 and 1, let's say, strictly. And this is actually how you show that the R liquid case works, by taking the quotient of this. And you can play a similar game where you have something over the sphere spectrum. So then you can wonder what you might have for different analogs there. This isn't expanded on too much. All right, next we're going to talk about something infinity categorical, animation. So if C is a category, generated under colimits, by a full subcategory, rather by the full subcategory, C, CP, CP here means compact projective. Then we define any C, so the animation of C, as the infinity category, freely generated under sifted colimits by these compact projective objects. So you can formalize this as some subcategory of the functor infinity category to anima. So what do we mean by anima? Anima, I mean animated sets, which is equivalently infinity groupoids or Kahn complexes, whichever way you would prefer. Schulze and Clausen call them anima. I'm going to stick with that for here because it's a nice term. Okay. So what are some examples of animation? Well, if you animate abelian groups, then what you get back is the infinity derived category of abelian groups. Rather connective. So this is why we sort of sometimes call this, you might have seen this before, called the non-abelian derived category. And we already talked about the animation of sets. So one thing we can also talk about is we can also talk about condensing a category where we use the same procedure as before, modulo set theoretic issues, which are there, but we don't talk about them for now. So we can also talk about condensing, and we can ask, how does this interact with animating? Well, in fact, you can prove that animating and condensing commute. And one thing we can talk about is condensed anima, which is just cond any, or equivalently the animation of condensed sets. All right. And one interesting thing to note is that if you take X and ECW complex, then this goes fully faithfully. Here I mean by the category of CW complexes. Here, let me just write CW instead. Into the category of condensed sets, which embeds fully faithfully into condensed anima. Here you can sort of think of taking everything in some Eilenberg-MacLane spectrum in degree zero, so some sort of degree zero set explicitly. Here you have some functor which is not fully faithful. To anima. This is taking, so some X is going to go to X bar. And when we go this way, we're going to call this X bar over here. Here, X is going over here to what we're going to call this geometric realization of X. And now these embed into condensed sets, but these does not commute. Okay. So how are we going to use this? That might be our question for now. Well, one thing we don't like is intersections. Intersections don't behave so well on the point set level. We really like to derive them. So we want to use some sort of derived algebraic geometry when building our theory of analytic rings. So that's why we're going to work with condensed, animated, associative rings. So we're going to make a new definition from earlier. Well, this is a new definition, but it's very similar to one from earlier. An analytic, animated, associative, so many words, ring. I'm going to abbreviate these as AAA rings, just because I don't want to write out analytic, animated, associative every single time, is a pair, AM, some condensed, animated, associative ring, a functor of measures as before. But in this case, landing in the pre-stable infinity category. Of derived connective A modules, such that for all C as usual, with our usual condition from earlier, there's a few equivalent ways you could say that. You have the standard RHOM argument for all extremely disconnected S. Is an equivalence of enema. This is just saying the same thing as before. And as before, you can define d greater or equal to 0 am. You can also talk about tensoring over A with am and all the usual stuff. Now, before I didn't actually define a morphism of the analytic rings, it works roughly as you would expect, except there's a slight technicality that you don't just define it strictly as some morphism of the underlying rings with some natural transformation. You define it as a morphism of the underlying rings such that the derived category of one pulls back into the derived category of the other, looking at the measures. So we can define that here. So a morphism is some underlying morphism of condensed animated associative rings. Such that for all modules n in this derived category here, the pullback lives in, which a priori only lives in D of A, is actually in M complete A modules. All right. So what are we trying to do with this? Well, what we want to do, a notion of algebraic geometry for classical analytic objects. So Banach spaces, Smith spaces, etc. So we want to import these. We also want our solid / adic spaces to fit into the theory. And one thing that I didn't talk about before is that schemes, so algebraic geometry, embeds fully faithfully into discrete adic spaces in two different ways, so you don't lose anything. And this sort of fits algebraic geometry and the new notion of analytic geometry all into the same context. So what we're going to do, we're going to use a functor of points definition. So a functor of points just means the unetta type argument. So considering everything as a sheaf of, well, rings up. So some functor on rings to set such that it satisfies some sheaf conditions. But before that, we only have this for analytic rings, analytic associative rings. But what about commutative rings? Because when we're doing algebraic geometry, we want commutative stuff. So we're going to need another definition. An analytic animated commutative ring is an analytic animated associative ring, AM, such that A is commutative. So by commutative, I mean it's an analytic animated commutative ring. And for all primes P, the Frobenius map induces a morphism of analytic animated associative rings from A, this measures M, to taking the derived quotient by P. Because that's where you would expect it for Venus to land, and we want this to just form some genuine morphism of these rings. So the morphism on A to A over P, that's easy, that's almost guaranteed. What the issue is you want to make sure that functors, which are rather modules which are complete with respect to this, actually pull back to those which are complete with respect to this. So why do we have this condition? Well, it's because we want something else. We want to talk about normalized rings. So an AAA ring or an AAC, analytic associative commutative ring, is said to be normalized. Let me call it AM. If A is equal to M of a point. So whenever we don't have this, we can always correct without really changing the module category to making A equal to M of a point. So normalized just sort of says this is canonical. So we have this, for example, with Z, comma, trivial measures. So trivial measures just means that M of S here, let me call this triv. I'm making this notation up as we go. This is not standard notation. So here, triv of S is just going to be Z of S. So this just means that we're taking the category of dense abelian groups, or rather the derived category of those. And this is normalized because triv of star is equal to Z. But you can ask, is the analytic ring structure determined by the ring if we require it to be normalized? Well, this is not true. Just by similar to examples that we had before. Because if we take Z and the solid modules, then Z solid of a point is still just Z. Same thing happens for liquid modules. Liquid modules still have R as the underlying ring. Those are all normalized, and basically everything we've seen so far has been normalized. So this really doesn't lose any information. This is just an extra technicality that we have to track. And there actually are some which are in general not normalized. There's some used in condensed, in analytic.pdf in the proof of the main theorem, which are not normalized, because if we're using the Z of t greater than R, I believe we use at some point Z, I think it's Z of t. So this one would not be normalized but we can normalize it without losing anything to just Z of t greater than R. We don't lose anything in doing this, okay? That's the main point. So with analytic animated commutative rings, it's not necessarily true that these are, or I don't actually know if it's known or not, if this Frobenius is required. I know it was also stated that it's not even known if this holds in general. So this holds in many cases. It's unknown if this holds in general. This might just be automatic. But the reason you need this is because when proving that you can normalize for an analytic animated commutative ring, you need to use some Goodwillie calculus, and this helps you show that some Goodwillie derivatives vanish. Okay. So now that we have this part of the theory worked out, we can talk about some specific classes of morphisms. Hang on, the lights just went out here. Let me just turn these back on. Okay. So we're talking about some specific classes of maps of these analytic animated associative commutative rings. So a map of analytic animated commutative rings is one of analytic animated associative rings which commutes with Frobenius. So we will call the category and ring, which I'm going to henceforth call analytic rings, because I don't want to talk about all the different adjectives. So this is going to be the category of analytic, animated, well, let me say normalized, analytic, animated, commutative rings. All right, so working in ANRing, we call a map, we're going to define two nice classes of maps. A map F from A with measures A to B measures on B is called steady. If for all base change diagrams, so this base change diagrams, I mean, this is a push out in analytic rings. So for all base change diagrams, the map from this functor to this one on the module categories. So this says that if I start here and go this way and over this way, or I go this way over this way, that these is an isomorphism. So this just says the base change commutes with push forward. That's how we characterize these steady maps. All right, next, a map from A with measures on it to B with measures on it in analytic rings is a localization if pullback is fully faithful. So what does this say? This says that here I have this category up here. Down here I have the same thing on B. And I can take the forgetful functor, and this is fully faithful. And because we always have this junction here, which by the way, I have not mentioned how to define tensor products when A is commutative yet, but you can. I'm just going to say that without any proof. And taking this tensor product here, this is a categorical localization. So this says precisely that the derived category of B modules is a categorical localization of that of the same for A. Okay. So what we can do is we can talk about steady localization. These are going to be important. Oh yeah, I haven't proved much of anything today. I'm gonna take a page out of Ballmer's book and steal one of his jokes and say, since today is a holiday here, the proofs are on vacation. So steady localizations are steady maps, which are also localizations. So localizations commute, or rather, I should say are stable under base change, So pushouts, which are going to be pullbacks when we move to the scheme sort of case, because then we're just taking the opposite and everything. These are stable under base change and composition. Steady maps are stable under composition and all colimits, in particular under base change. And one more fact. A localization is an epimorphism. And if F is steady, the converse holds. So since we have a little bit of time, we can prove this. All right. So to say F is in epimorphism, what we're saying is that if we form this push-out diagram, then G and H are isomorphisms. Now, in order to see this, what we do is note that if F is a localization, implies it's a localization in the categorical sense, so F star is fully faithful. Implies that the co-unit of the adjunction that this determines is an isomorphism. So in particular, the natural map from M to M tensor over A with BMB is an isomorphism for all B modules M. So what this tells us in particular is that BMB, any object, so here I really am meaning this evaluated on some extremely disconnected, but what we can do is we can note that this is isomorphic to this as modules. And then if you examine the construction with how to build the actual derived category for this, you realize that it is literally just giving you back the derived category for this, so that this here is in fact an isomorphism. Skipping on a few of the details, but filling those in is an exercise. All right, conversely, if F is steady, then we can look at this same map here. So if F is steady, and G comma H isos without loss of generality identities, then by definition of F being steady, we have that the map from F upper star, F lower star to the identity on derived category BMB is an isomorphism. So this in particular says that we're looking at this adjunction here. It says that the co-unit, right, you have to do a little bit of work to check that this actually is the co-unit, and that does agree. But I guess sort of by naturality, you can sort of see that it would make sense for it to be a co-unit. I'm not going to delve into too many details on that, but sort of since this is all a very natural story, co-unit is an iso, implies F star is fully faithful, which by definition says that F is a localization. So in particular, steady localizations are stable under all colimits because epimorphisms are and steady maps are. Okay. So now we can come to our main point. We equip analytic rings opposite with a site structure where coverings are finite families I'm going to define this analytic spectrum notation in a minute. Where the maps from AM to AIMI are steady localizations. Here we're in the opposite category, so that's why these arrows are reversed. Such that the map from the derived category of A. I didn't mention this before, but you can remove the greater or equal to 0 here if you're willing to stabilize these infinity categories, which we normally will. I'm just going to do that here because why not? I mean, there's a way you can stabilize in a pre-stable infinity category. So it's literally just what you do there. This way you actually get something back that's stable, which is really what we want to do and what we want to work with at the end of the day. So we want this to be conservative. So that means that if it takes something to 0, then it's 0. So it sort of says that it does form a cover. So you can think of this similar to like the Zariski case, where there actually will be possibly a little bit more, but you can sort of think of these as actual localizations of rings. And this condition here precisely says that it covers all of the different prime ideals in the spectrum, if you're thinking about the Zariski case. Okay, so now we're going to talk about sheaves on and ring up. Particular, we have a proposition that says that the analytic spectrum of an analytic ring. So this is going to take the MB to analytic comms from AMA to BMB. This is a fully faithful inclusion of an ring up to sheaves of enema, so infinity groupoids on and ring up. All right. Next, we're going to define what we call, so for certain sub-pre-sheaves. So by sub-pre-sheaf here, I mean that the fibers over any point are either empty or contractible. So this is a steady subspace. If it is the image of some coproduct where each of these maps the other way, is a steady localization. All right. So with this in mind, we can talk about for general presheaves. This is a steady subspace. Or for general sheaves, it doesn't really matter. Let's say for general sheaves. Yeah. So some subsheaf here and some subsheaf on this one. You can show that it sort of doesn't matter so much in that the sheafification of the colimit will always give you back something which is steady. So this is a steady subspace if whenever we test with some affine, the pullback here is going to give us some steady subspace of this affine. So this sort of just defines everything by a base change. Finally, we can define an analytic space. So an analytic space we define to be a sheaf on analytic rings, the opposite category there with our site structure we defined before, such that it can be covered by affine steady subspaces. So that is to say steady subspaces which have the form of these analytic spectrums. All right, that's all I have for you today. Any questions?
Let's thank our speaker.